The questing minds of ancient Greece probed the structure and behavior of their Mediterranean world. To them, everything was made of varying combinations of what they called the four elements: water, fire, earth, and air. Then, over 2,000 years ago, there was inspiration.
It is not enough to speak of the elements. They tell nothing of form. What matters is the form of matter. Look at the sea, this shapeless liquid mass. Does its substance have true form?
Or structure?
Exactly. See how it may be broken into smaller and even smaller particles. Is there no end to how far this watery matter will subdivide?
Consider these endless grains of sand, the perfection of infinity. And yet, perhaps there is some basic speck of matter which can be made no smaller.
The undividable essence of matter, of the elements, the atom.
The ultimate part, which is in itself partless.
Maybe, exactly.
An inspired guess that came remarkably close to the truth. It would lead, centuries later, to the birth of chemistry. How is it that one substance, through the action of nature or of man, may be changed into another? Now, man seeks to solve the mysteries of matter by using the science of chemistry. The chemist takes the world into the laboratory to probe the elements of change. The ancient Egyptians also held to a belief in the four elements. They lacked the Greeks' curiosity about matter, but they were expert manipulators of materials. They had a technology. Egyptians were skilled in metallurgy: iron, copper, bronze. They learned to heat the desert sand with soda and lime to produce beautiful, useful glass. They had decorative glazes for ceramic vessels, which could contain Egyptian beer. How to brew it was known. The chemistry of a carbohydrate's change to alcohol was not. In the Orient, there were artisans in metal. Sword-making, a ceremonial art, performed in spite of ignorance of atoms or molecules, or of what a sudden change in temperature does to the crystalline structure of iron. Men simply knew how to make a sword that would last. But the metal most prized for its luster, its malleability, its resistance to rust and corrosion was gold. It was the quest for a way to change other metals into gold that gave rise to the magical art of the Dark Ages, alchemy. In secluded, smoke-filled workshops, the jealously guarded secrets of the alchemists were practiced and elaborated. Men sought a universal, perfect principle, to purify life by freeing it from disease and death, to purify matter by elevating it to gold. The precious metal itself was fairly readily purified, for it is not very chemically active. Simply heating impure gold in a porous crucible will cause the impurities to be absorbed by the substance of the container, leaving a shining globule of molten gold. Alchemy was not a true science, but only haphazard experimentation. However, in the alchemists' workshops, there grew a useful body of knowledge about various substances. It could be demonstrated, for example, that if a red powder called cinnabar is heated, it will produce the silvery metal mercury. The alchemists considered mercury as a symbol of one of the same ancient elements: earth, water, air, and fire. This alchemist, Hennig Brandt, actually isolated what modern chemists would call an element, phosphorus, one of the 100 or so substances from which all other materials are formed. The chemist, measuring weights and energies, today studies how the elements combine and what they produce. Prediction and control of chemical change depend on knowledge of how the reacting substances are structured. Conversely, carefully observed chemical changes helped reveal the structure of matter in the 18th and 19th centuries when modern chemistry was born. One of its fathers was Lavoisier, who introduced something new. He measured the amounts of all substances involved in a reaction. This quantitative approach revealed that in a chemical change, matter was neither created nor destroyed. There was only a rearrangement of components. Lavoisier's theory, the conservation of matter, explains this experiment. The candle goes out before the water reaches it, because it uses up oxygen by combining it with other elements to produce carbon dioxide. The water will rise because it removes this gas from the air by dissolving it. So, air pressure outside can force water into the available space. Robert Boyle redefined an element, a substance that cannot be separated into any others, but which may combine with other elements to form a compound. John Dalton modified the Greek ideas and produced the modern atomic theory. Taking Boyle's definition of an element, he proposed that all matter is formed of building blocks called atoms, and that each element has only its own kind of atom with a specific atomic weight. Then came the Russian, Mendeleev, who arranged by ascending atomic weight all the elements known to 19th century chemists. He found that they could be grouped into families with similar physical and chemical properties in what is called the periodic table of the elements. In one family of metals, lithium, sodium, and potassium have similar physical properties. All are soft and malleable and have metallic luster. Members of this family have slightly different densities, but compared to other metals, all of them are light. They also have similar chemical properties. When each metal is heated with chlorine gas, there is a chemical reaction that releases energy and produces a compound. Lithium and chlorine combine into lithium chloride. Sodium, a metal, and chlorine, a poisonous gas, react to produce common table salt, sodium chloride. Potassium produces a similar salt. Mendeleev's great insight was to leave gaps where no elements of certain atomic weights had yet been found. Each gap was eventually filled by the discovery of an element with the predicted atomic weight. Lord Rutherford helped explain why the periodic table works. At McGill University, the New Zealand chemist studied atomic disintegration. He proposed a basic atomic structure centered on a nucleus. It has a number of positive charges and most of the atom's mass. Outside it are an equal number of negatively charged electrons. The number of positive charges in the nucleus gives the atom and the element identity. The number and energy of electrons governs chemical properties. This explains why lithium reacts with water in much the same way as the other members of its metallic family. In the outer region of the atom of each of these metals, there is a single electron to be lost or shared. Modern chemists have learned much about the atomic structure of the elements, how their structure affects their chemical reactions. In any atom, like charges repel, opposite charges attract. The electrostatic attraction between positive nucleus and negative electrons holds each atom together, or bonds two or more to form a molecule. There are millions of times more molecules in one drop of water than there have ever been people on Earth. Every water molecule has one atom of oxygen and two of hydrogen, held together by the attraction between positive and negative charges of nucleus and electrons. Molecular arrangement determines physical state. When ice absorbs heat, water molecules are given enough energy to break free from their place in ice crystals and to begin random motion as ice melts to water. If molecules absorb enough energy, they fly off in all directions as the liquid becomes a gas. Now the four classical elements can be seen as the states of matter: solid, liquid, gas, and the energy that causes physical change. Sugar is a compound of carbon, hydrogen and oxygen. Adding acid to sugar causes another kind of change, chemical change, in which atoms are rearranged to form new molecules. This reaction produces molecules of water as steam and leaves atoms of carbon. There are then two kinds of change. When the element bromine evaporates from a liquid to a gas, that's physical change. The same molecules speed it up. But when hydrogen burns in bromine, there is chemical change. Atoms are rearranged to form molecules of a compound, hydrogen bromide. This plastic balloon will be filled with chlorine and hydrogen, each in the form of gas. No reaction occurs in the dark. Here, the energy required to bring about a chemical reaction between them will be supplied by light. Each gas's molecules consist of two atoms. In the dark, only a few molecules are split into single atoms. But light supplies the energy to break chemical bonds. When an atom of one gas collides with a molecule of another, what's produced is a different molecule. The amount of energy available can change the speed of a chemical change. Rust is the product of the slow combination of iron and oxygen. With a red-hot steel wool, iron combines with oxygen fast enough to burn. Fire releases energy in the form of light and heat, energy that could be converted into motion. In this age of nuclear power, man has begun to harness the energy released by another kind of change, within the atomic nucleus itself. Early chemists were wrong. The atom can be split. But the alchemists, in a sense, were right. Bombardment with high-energy particles, accelerated here, can change one element into another. By changing the number of positive particles in its nucleus, an atom of base metal could be made into an atom of pure gold. Chemistry has revolutionized how man uses the materials in his environment. Traditionally, boiling the right plants produces dyes for Harris tweed. Now, instead of having to rely on natural pigments, chemists synthesize dyes. Substances with different molecular structures will produce different colors. Chemists can design molecules and produce, for example, 3 substances with which to treat these samples of fiber. Then, 3 samples of the same fiber can be put into the same dye bath and come out with 3 different colors. It's all a matter of using chemicals with the appropriate molecular structure. Most substances, such as copper, are seldom naturally pure. Electricity can extract pure copper from an impure mixture. the impure plate on the left transfers only copper to the plate on the right. In this process, called electrolysis, as the current is passed through, charged atoms of copper are released from the positively charged impure plate and travel through a solution to be deposited on the negatively charged pure copper plate, 99 and 99/100% pure. This molten copper, naturally mixed with oxygen, will form the impure plates. A green log supplies carbon and hydrogen to remove much of the unwanted oxygen as steam and carbon dioxide. This partially refined copper is then poured into molds to form the impure plates for electrolytic extraction of pure copper. This powdered nickel ore consists mostly of nickel oxides with traces of other metals. Pure nickel can be extracted by passing two gases through the ore. Hydrogen molecules pick up oxygen from the nickel oxide to form water. Carbon monoxide then picks up the nickel atoms, which can be recovered as pure metal by driving off the carbon and oxygen. Chemists not only extract materials, they synthesize them, imitating nature with synthetic silk. The silkworm eats mulberry leaves and transforms the leaf cellulose into protein fibers of silk. In the mid-1800s, man tried to duplicate the process. Now, since the turn of the century, industrial chemistry has been able to take cellulose from wood pulp and to transform it into strong synthetic threads of rayon, the first man-made fiber to be used. Deadly nightshade, an ancient remedy that turns out to contain atropine. Chemists have now isolated the active substances in many herbal medicines. Digitalis from foxglove, quinine from cinchona bark, opium from the poppy. In medicine, as in industry, chemists can not only identify and purify useful substances, they can synthesize them by literally building a molecule of the right shape and size. This is how one of the sulfa drugs works. A small piece of paper soaked in sulfanilamide is placed in 1/2 of a bacterial culture. The substance interrupts the life chemistry of bacteria. Around the paper, none survive. The sulfa molecule on the right is almost identical to that of a substance vital to bacterial life. It is shaped to fit exactly onto a bacterial enzyme and to stay there, thus preventing the natural chemical from reaching the enzyme, and the disease organism dies. Chemistry has now produced many drugs by extraction and synthesis, each with specific effects on the body or the mind. LSD. This is the plan of the molecule that has such a drastic effect on the human brain. But LSD's hallucinogenic properties can be eliminated by one minute change in its molecular structure, the addition of a single atom of bromine. Slight changes in molecular structure can produce extreme changes in chemical property. The green pigment in plants, chlorophyll, has a molecule like this, with magnesium at the center. There are certain crabs whose blue blood contains a substance with a similar molecular structure, with one small difference. The central magnesium atom is replaced with an atom of copper. The same molecule will form the hemoglobin in our own red blood, with the substitution of an atom of iron. Chemists can produce substances that are usually manufactured only by living tissues. And some people wonder if chemistry might not someday be able to reproduce life itself. Chemists have already cracked the genetic code by discerning in the giant DNA molecule the slight changes that make every individual unique. But does anyone have the right to manipulate heredity, to create or destroy life? Chemists continue to probe the atomic and molecular basis of matter, seeking to understand and control the fabric of our world. As man's knowledge of structure and change grows wider and deeper, what new insights into the nature of reality will be revealed? And how will man change his world and himself?